Welcome to Python Labs. In this video, I am going to cover some very important topic on dimensionality reduction using heat maps. Now, before I go into the actual code, let me explain a bit of an overview of what is dimensionality reduction. Now, in the real world scenario, assume that you got so many features, maybe 30 columns or 50 columns or even sometimes 100 columns. Then in that kind of scenario, it is quite obvious that not all the features might be important. So in a way to reduce the number of features and just identify the most important features, we call it as dimensionality reduction process. So basically dimensionality reduction is the process of identifying the most important features and either reducing or in other words removing the least important features. So this is what by definition what dimensionality reduction in data mining is all about. Now dimensionality reduction, it is part of the pre-processing technique because as part of data preparation and pre-processing you have to do the dimensionality reduction as well before you start applying some very important algorithms and so on. So in Python we have some very amazing chart or the called seaborn heat map. With the help of this map, we can find all the correlation matrix among all the features in a row by column matrix, and in that way we can identify which are strongly correlated and which are least correlated, and the ones which are strongly correlated we can actually drop them, most of them. So that's basically what this concept is all about. So let's jump into the code. So the very first step is to import the needed libraries. I'm basically running my code. Let me increase the size here. Okay, so I'm running my the first piece of code is about importing the needed libraries, the numpy, the matplotlib, the pandas and the seaborn. So I'm just going to run it. So that is my step 1. My step 2 and 3 is basically I'm going to read the CSV data on which I will be applying the dimensionality reduction, and then I will also try to have a quick overview. This is actually the best practice, as I keep mentioning in my videos, that always try to have an overview of the data, see the basic stats, because that itself can explain a lot, and if there are any anomalies or some abnormal data, you can actually pick them up pretty much from here itself. So this is basically one of the best practices. So let me show you. So I'm going to run the second one, which is read the data from the Excel file. So I'm reading the data from the Excel file, which I have actually performed as part of my previous video about how to identify outliers. And after fixing the outliers, I exported the data in a CSV file. I'm pretty much reading that CSV file. And now I'm going to have an overview of how the data looks like. So this is how basically the data is looking like. I have the sex, age, weight, comorbidities, post operation, length of stay, and total length of stay, readmissions, and so on. These are basically the columns that I have already got in this particular data frame. So once I have got this in the data frame, now the one of the easiest, there's a beautiful matrix that we can find out the correlation between all these features. You can pretty much run with this code, which is basically called data frame.correlation. Now if I run this data frame.correlation, it will show me all the column by column. You see here, for example, age by sex, age by age, age by weight, and it is also showing me how much they are correlated. Obviously age by age is going to be 1, which means it's 100% correlation because it's the same feature. But if you talk about age against weight, it is 0.25, like 25% similar correlated, and so on. But the problem with this kind of correlation matrix is the data is very cumbersome and it's very difficult to understand. You see here, this is really difficult to understand and to go through each one of them one by one. So what we do after this one, like as I said, overview the step 4, which is viewing the correlation matrix. What we can do after this is we can actually view the correlation matrix in the form of a heat map. What we call as heat map is basically, this is what I'm trying to say. So there is a beautiful chart. Again, I strongly recommend you to read all the maps that I'm mentioning in my videos, to go and view the official website, which is basically, for example, if I go into this particular website here, so I go here and I go basically like, I look into that one. So let me, yeah, this is the seaborn.heatmap. Seaborn.heatmap, again, you can see all the parameters that are needed, which we can pass through. So this is basically the chart that I'm going to use in my particular example. So what I'm going to do is I'm going to view the matrix in the form of a heat map for better visualization. So what I have got here is the code, simple piece of code. Just please try to watch my previous video about data visualization if you really want to understand the different types of amazing charts and graphs we can generate with the help of this seaborn Python library. So again, I'm setting up the size here. That's basically like I want the size of 30 by 30, and then I'm basically the same thing what I have written here, this particular thing, data frame dot correlation, which is basically x by y matrix, this particular matrix. I'm storing that matrix in a variable called correlation data frame df, and then I'm passing that as my data in a heat map. What is my data? It's basically df.correlation. You could have written directly here df.correlation. It's up to you. And then I'm basically saying, would you like to have the annotation? Yes, true. And then the line width, between the lines, please, I recommend you to go through these parameters here. All I'm specifying is basically some of them, not all of them. Like data, the one that I'm using, and for example, line width, this is the one. So you can use most of those parameters. You can set accordingly, and color as well. I'm actually setting the color as blue. And then when I say plot.show, and if I run this piece of code, you can see that it generates an amazing chart, a matrix. You see here, this is basically what I'm trying to say here. So this is showing me, so once I run this code, this piece of code, then it shows me a beautiful column by row by row by column with all those features, x and all the features, and how they are correlated. Now after we got this n by n matrix, we can see that, for example, in this particular example, the way heat map works is the ones which are strongly correlated, it shows in a very dark color. You see, the darker the color, which means that the strong they are correlated. Now in this particular example, I will focus on this particular value here, which I have mentioned here as well. So for example, in this diagram, the T loss, which is basically total length of stay of patients in the hospital, and post underscore O loss, which is post operation length of stay, you can see that the value is 0.97, which literally means that total length of stay and this column, which is post operation length of stay, those two columns are very strongly related, which means we don't need both of them. The ones which are strongly correlated, we just need one of them. This is point number one. And point number two, another thing you will notice from this particular diagram, that there is one column called total operation, and pretty blank, pretty empty here. Now you may be wondering why this is blank. You see, this is another kind of a question, why this is blank. The answer is, it's very valid reason. The answer is basically, if you look into the data set for that particular column, the column name was, what was the name of that column? It was this one, total operation, T operation, right? T operation. And if you look into the T operation, you see here, basically what it is saying is, I just have one value throughout the column. Let me open up this Excel file to make things even clear. So let me open up this Excel file. You see here, I will basically show you what I mean to say. You see here, this total operation, this particular column, if you see here, now let me convert this file into a table to make life easy, and insert table. Now let me just focus on that particular one, which is pretty much here, T operation. If you notice that there is only one value, I mean, this particular complete column has just one value, which means it's not important as well. There is no correlation happening in this particular case. That's why this is basically showing us in the heat map as a, and also if you see in the matrix as well, it's saying nan, empty. And the same thing here in the heat map as well. You see there, this is basically total operation by total operation. It is not showing any correlation because it's a single value. So in that kind of scenario, when you have that kind of scenarios, First things first, what we need to do is we don't need that kind of columns which are just having single values. So we can simply drop them from the data frame dot drop and that particular T operation, and I want to apply the changes at the column level. That's why axis equals to 1. I have already explained all of these things in my previous videos. So once I run that code, for example, I don't need this T operation because it's just holding one value. There is no unique values like the other. For example, here, for example, perforation, there is a 0 and 1. For example, the pus formation for the patient, it's 0 or 1. But in this particular case, it's just one value. So what we can do is we can safely delete this particular feature, because and this can help us to reduce our dimensionality. So I have basically described, which is a best practice again, to find out what are the values. And now I'm going to drop this feature. I don't need this feature. So now that I have dropped and I have updated my data frame, if I go back and again I rerun this heat map, look what is going to happen. Now please pay attention. Before we had how many? We had 30 columns, right? Now I'm going to run this heat map again. This time, because we have deleted that one column, so that column is no longer there. You see there, the T operation, that column is gone. Now that we have a beautiful heat map, now again in the heat map, if you want to change this color, it's up to you. But for example, if I want to change this to greens, again I can run this again. It will look in the green color. It's totally up to you. This is how you can change the colors, and the colors are quite good, very nice. It's totally up to you, what colors you want. I'll just go back to blues. So anyway, so now that we have done this part, which is basically deleting or dropping the features with holding just one value, that is basically what we have done in step number 6 and 7. Verify and drop single value features, because it really makes no sense when there is only one value in that feature. So step number 8 is, now this is the most important part. Now what I have got here is a very beautiful piece of code. Actually I had to do quite a lot of research, and I found this piece of code by searching online. And what we are doing here is basically we are trying to go through, because this heat map has so many features. You see here, we are going through, what we are doing is we will go through each of these columns, and then we go through each of the row values, and then we will see if the values are more than the provided say the maximum percentage of correlation. In this particular case, what we are saying is it's 97% correlated, right? For example, here the weight against this particular column, what is this column? Weight against age. For example, the weight against age is 0.25% correlated. So we have to specify, this is something that we need to define, what kind of percentage, what we call as threshold, above which we can simply delete the features. In this particular case, we know the total length of stay and the post operation length of stay, they are 97% correlated. So which means we just need one of these two. We don't need both of these features, right? So that's basically how this code is working. So I have got a nice function here. I defined a correlation function. I passed the data frame or my data set, and I'm setting up what is the maximum correlation that I want. Okay, so first I'm holding a temporary set here, and then I'm in the feature correlation. This is again the same matrix, data frame dot correlation, the one that we have already defined. This is the one, this feature, data frame dot correlation. That's exactly what it's doing there. So we are going through all the columns, and in each column and each row value, in each column, each row value, basically like column and every row, we are finding if the value is greater than the maximum correlation we have specified, then hold that value, take into consideration, because these are the correlated features which are not needed. We can simply return these values, and once we return these values, we can simply delete those correlated features. You see here, basically the same thing. If I'm going to run this code again here, I'm going to run, I have executed up to here. Now this is the function that I have created. I will run this correlation function. Now once I have created this function here, now I'm going to make a call to that correlation function and hold all the strongly correlated features for deletion. Okay, strongly correlated features, and also I'm viewing the list of features which are strongly correlated, which means I don't need. See here, T loss, because we know T loss and you see here T loss and the post operation length of stay, which is 0.95. T loss, because this is a column, post operation length of stay. You can, by the way, you can delete either this feature or this feature as part of dimensionality reduction. Either of them, not necessary that you have to just delete this or that, but in the loop, in the function that I have created, it basically takes into consideration only the post, because I'm going column and then by row. That's why post operation length of stay, it is keeping that one, while the total length of operation, it's saying that this is not needed, we can reduce the dimensions. So that's basically what it is showing me here. In the here I have said, for example, anything more than 80%, you can even say 90%, for example, anything above 90% or 80%, you can even, like for example, if I say just for the purpose of this video, I will run this one. Anything above 50% I consider as strongly correlated. Then there are two dimensions or two features that we can get rid of. But in a practical sense, we don't want to go up to 50%, maybe a bit higher. So I will say that maybe 80%, anything above 80%, I am interested in getting rid of those features as part of dimensionality reduction. Now that I'm having this list of all the dimensionality, in this particular case only one dimension, so I'm simply going to make a call, basically data frame dot drop that particular column. If it is having more than one column, it will, those columns, whichever the columns are, and I'm just dropping it and updating my data frame. Once I run this, now again, if I rerun my data frame to just check here, what are the pending columns, the new set of columns, it is 28 columns. If you remember, at the beginning, we started with how many? We started with, we had 30 columns. In that 30 columns, one column we identified that it is basically having just one value throughout the this one, which is just having one single value. There is no other values. That's why there is no correlations. So that means this complete feature itself is not needed. So we deleted that feature. That was the first step we did. So we reduced one dimension by dropping that one. And the second step, what we did is basically identifying all the features which are greater than certain correlated strong correlations, which is in my case here I have specified as 80%. You can specify 90%, 70%, totally up to you. And we got rid of one more dimensions. So in this way, we have actually reduced from 30 features to 28 features. But in some real world practical, this is a real world scenario, by the way, but in other scenarios, you may even reduce a large number of features with this kind of small technique. And this is one of the best practices that we must do as part of data preparation or pre-processing. And if you are interested, you can add, again, you can export the results into the correlation Excel file. For example, here I have exported into a CSV file. So if I run this one, and I can go back and I can see my new basically, like, let me open this one. This is the new CSV data that I have exported with those two features. We removed those two features. So I hope this is clear now, and I hope you have understood how beautiful it is to easily predict, and how easily we can detect all those features which are strongly correlated, and we can reduce the number of correlations, so that the less the number of dimensions. In other words, we are focusing on the most important features, and then we can perform the remaining steps of data science and machine learning. Thank you, and thank you for listening.